alaikum. Today we are going to explain about the axial loading of compression. Our group members today are Tanupat Liman and Nick Sulaiman and Khamis Al-Jahbitar.
For the first one?
For the first part, design of compression members. Short and long columns, buckling load and buckling failure modes, elastic and inelastic buckling, local buckling, design of compression members, and effective length of rigid frames. Next, axial loaded compression consists of columns and struts and top chords of trusses, diagonal members of trusses. Columns and compression members are often used interchangeably. Commonly used in WH shapes, square and rectangle or round HSS, ties and double ties, angles and double angles, and channel sections. Columns, failure mode, limit states, crushing and flexure or either buckling or local buckling. Thank you. This is my part. Next, will present as Tanuk part. Pause.
Today I will present about the short columns. Okay. The compression members. We have to know that the structure elements that are subjected to agent compressive force only are called columns. Columns are subjected to axial load through the centroid. We have known that when we apply the force between the point from the top or bottom, we can find the result. We can find the force between the contact force that we apply, which is it can be happen at the centroid. We can call it as compression is axial loading. Then what is stress? The stress in the column cross section can be calculated as F equal P over A. What is F? We have known that F is a force, P is a pressure, A is area. Long columns. Long column is level matrix. It will be non-uniform due to accidental eccentricity of loading with respect to the centroid member of straightness, coherence, or residual stresses in the member cross-section due to fabrication process. However, these are secondary are usually ignored. Bending moment cannot be neglected if they are acting on the member with agent compression, and bending moment are called beam column. The larger the slenderness ratio L over R, is greater the tendency to buckle under smaller loads. So fraction tendency to buckle and condition under eccentricity, concentric and eccentric loads, imperfections in initial coherence, out of plumbness, residual stress. Likely can be one or both axis major or minor axis. Column buckling. We can consider a long slender compression member. If an energy load P is applied and increased slowly, it will ultimately reach a value P critical that will cause buckling of the column. Pressure critical is called the critical buckling load of the column, which means where the pressure is being applied with a slowly reaction, it can be over the critical over here, then it will be banned. This is buffering loop. The result that we have been applied, we will get the bending of like this. So we have a formula to find the P-critical load. M is equals to minus P deformation. M became known is as a moment, and negative P is a force and the deformations. As we can write the relationship between the deflected shape and the moment M, we have to differentiate it. D squared deformation over di squared equals to M over Pi equals to negative P critical deformation over Ei. As we substitute, the final answer will be P critical equals to pi squared Ei over L squared, which means this pi 3.421, E is E and I over L2. Then I pass to Terumpat.
Okay, from the next, talking about the previous slide. So this is the formula for the 5P. P is the direction. This one. This is the direction of the deformation. So we can assume the y-axis, or because this not that one, but the deformation and x, and we got the pressure both sides of this object. So it makes the bending from this formula. So the next is the column wrapping. Column wrapping is occur when the said column subject to axial compression suddenly undergoes bending as shown in the figure 1b. Okay. And wrapping is identified as the failure limited step for the column. So the critical wrapping load or PCR for column is the theory given by equation PCR is equal to pi squared Ei over KL power 2. I is the moment of inertia about the exit wrapping. So K is the effective length factor based on the boundary condition. This is the table we give you. K and KL is the distance between inflection point in the column. K is the effective length factor. So we can see from the picture, this is K and KL is equal to depend on L. L is the column unsupported length. So now we next to the example. So this example is to determine the bucking strength of the Y 12 times 50 column. Its line is the length is L. So L is 6. So for minor axis, bucking is it is spin at both ends. For minor axis, bucking is spin at both ends. So what that means? So you can see that point and that point, there will be spin and make it like bending, like bending. So is it the spin at one end and fixed at the other end. So the first step is visualize all the problem for the weight or the width, the width of the flank section is 12 times 50. So X is the major axis and Y is the minor axis. Major axis means axis about which is the has greater moment of inertia. So Ix must be greater than Iy. So step 2. This means the effective length according to the table. Okay. For pin to pin and condition about the minor axis Ky, they give us Ky equal to 1, the theoretical value, and Ky is 1.0 is recommended design value for pin fit and for pin fit end condition about the major axis, and Kx is 0.7 theoretical value and Kx is the 0.8. So this is from table. From the refer to the table of the K. And next is according to the problem statement, the unsupported line for the graphing about the major x-axis equal to the major x-axis is equal to Lx and equal to 6 meter from the question. And the unsupported lines for the graphing about the minor y. So it means Ly is also 6 meter. And effective lines for the major x-axis graphing, this is find effective from the formula I told you before. This Kx is equal to KL. So in x-axis we find Kx and time Lx is equal to 0.8 times 6 is equal to 4.8 meter. In y-axis also do the same thing. In Ky times Ly is equal to, the value is 1.0 times 6 equal to 6 meter. And the next step, it means the relevant section property. So elastic module of elastic is mean the value of E is equal to 200 gigapascal constant for all steels. For white 12 times 50, this Ix is the moment of inertia of X is equal to 163 times 10 over 6 millimeter power 4 millimeter 4 and moment of inertia in y-axis is equal to 23 times 10 over 6 millimeter 4. So step 4 is now is the calculated of the backing strength. Okay, for the critical load, for the now define the critical load or PCR in x-axis. Okay, now we use the formula from I told you before. This is use the P equal PCR in x-axis is equal to pi over 2 EIX in E times E times I multiplied by in the moment of inertia in x-axis over by Kx and Lx. Now we substitute the value in the formula. So now we get the value in the kilonewton for P in x-axis. the critical load in the x-axis, and do the same thing in the critical load in the y-axis. So now we got two. We get we get two value of the critical load for the braking. So we need to find the braking strength of the column. Is the braking strength of the column equal to smaller. So that means we have 2 points. 2 points in the x-axis and y-axis. Is equal to P equal to PCR. So that means PCR is equal to 1261 because this is the smaller value. Because the braking strength of the column is to find the smaller value of the loading of the critical. Is the minor y-axis braking is common. Okay, note for the minor axis braking usually common for all doubly symmetric symmetric cross section. However, for some cases, major x-axis braking can common. So the steel yield strength was irrelevant for the calculating this braking strength. So this is the last slide for us. Okay, thank you very much.